السلام عليكم ورحمة الله وبركاته. بسم الله الرحمن الرحيم. Inshallah, in this lecture we are starting a new session 10, and it is still related to session 9, which covered hypothesis testing. In the previous session we assumed that we are given a sample of data and we want to test if that sample is generated from a specific distribution or specific population. But sometimes data scientists have two samples, not just one, two samples of data, and we want to test whether they came from or generated from the same distribution or the same population. This is called A/B testing. So in A/B testing, we are comparing two samples, values of a sampled individuals in group A, and we want to compare that with values of sampled individuals in group B. That's why it's called A/B testing, because it's because of the labels of the samples A and B. And the question is whether these two samples come from the same underlying distribution or the same underlying population. To answer this question, we will perform a statistical test called A/B testing. Let's apply that on a real example. The example is called maternal smoking. So in this example or this application, we have information from a maternity hospital. The information is related to newborn babies from mothers who were either smoking or non-smoking. So we have two groups of mothers who gave birth to newborn babies. Group A are the mothers who smoked during pregnancy, and Group B are the mothers who did not smoke during pregnancy. And the question is there a difference of the weights of the babies in these two groups or not? Or in other words, could the difference be due to chance alone? So when we see the example and we see the data, we'll see that in fact there is a noticeable difference between the average weight of the babies who were born to smoking mothers, and the average weights of babies born to mothers who were not smoking. So the question is whether this difference is just due to chance alone, or there is another reason or another factor that affected the weight of the babies. So in hypothesis testing, the first step is to set the hypotheses. So what are the hypotheses here? The first one, which is as usual the null hypothesis, is that both groups came from the same distribution, came from the same population, which means that the average weights of the babies were just different because of randomness, due to chance, due to the way that the mothers were selected in the two groups, nothing else. But the alternative hypothesis states that the babies of the mothers who smoked weighted less on average than the babies of non-smoking mothers. These are the two hypotheses that we will consider in our testing. The null hypothesis states that the average weight of babies in both groups are same or different just due to chance, and the alternative is that the average weight for babies from smoking mothers is less than the average weight of babies of non-smoking mothers. The next step is to determine the test statistic. So remember that we have two groups, A and B, A the smokers and B the non-smokers. What could be a reasonable test statistic? We want to compare between two groups, right? What should we compare? We are comparing the average weight of one group versus the other, and we want to see if one specifically is less than the other. So a normal choice of a test statistic is to get the difference between the average weights. So here we chose to subtract the average of group A, which is smokers, from the average of group B, which is non-smoker. So the average of non-smoking mothers, the average weight for non-smoking mothers, minus the average weight for for babies of smoking mothers. Now, if we got large values from that statistic, what does that mean? So a large value means that the average of smokers, average of babies from smokers, is larger than the average from non-smokers, or in other words, the average of non-smokers is less than the average, is much less than the average of the babies from smoking mothers. So large values here means the alternative. The large values of the statistic favor the alternative. Keep that in mind, because as you noticed from the previous session, this is very important when it comes to compute the p-value, because we want to know where is the direction of the tail, and thus compute the p-value and compare it with the significance level. Now, the next step is to simulate under the null hypothesis. Remember, we have two samples, we have two groups, smoking mothers and non-smoking mothers. We want to simulate under the null hypothesis. What is the null hypothesis? The null hypothesis is saying that the two samples come from the same distribution, come from the same population. What does that mean? It means that whether the mother is smoking or non-smoking doesn't matter. So the weight of the baby doesn't depend on the fact that the mother is smoking or non-smoking. That's actually the meaning of the null hypothesis. Both came from the same distribution, so the label of smoking or non-smoking doesn't matter. So we can get rid of that label and then sample from the mothers, getting two samples. One will be assigned to group A and the other will be assigned to group B randomly, because we assume in the null hypothesis that they come from the same distribution. So we can just get rid of the label, sample randomly from the population of mothers that we have, assign some of the mothers to group A and some to group B, and compute the averages of both groups. We can do that also by shuffling the labels, just to keep the size of both groups as in the observed sample. Okay, so we can either sample randomly from the mothers without looking at the labels, or similarly or equally, we can just shuffle the labels. Okay, shuffle means do permutation, random permutation of the labels of the mothers, so that we can then get a sample, assigned sample to a smoking group and assigned sample for non-smoking group. I will repeat that again so that I make sure that you got the point. So what we will do is, or what we want to do, is to get rid of the labels. So we can get rid of the labels because the null hypothesis says that the labels don't matter. We get rid of the labels, we sample randomly from the mothers, assign some of them to smoking, some of them to non-smoking. Equally, we can just shuffle the labels of smoking and non-smoking. It's the same effect. Okay, stating that in a more formal way, if the null is true, all rearrangements of birth weights among the two groups are equally likely. So the plan is to first shuffle all birth weights, or equally shuffle the labels, doesn't matter. Assign some of the mothers to group A and the rest to group B, maintaining the two sample sizes. And one way of maintaining the two sample sizes is just to shuffle either the weights or the labels. Find the difference between the averages of the two groups, and repeat that multiple times as we did before. So that is the plan. Now let's do that in code and see if for the case that we have, the specific case that we have, whether we will be rejecting or accepting the null hypothesis. So let's go to the code now. So this is the data that we have. The data that we have, as you see, has multiple columns. Each row here is a mother-baby pair. What we are concerned with from this table is just two columns, the birth weight and the maternal smoker. That's the label of the mother. Okay, so we'll just select these two columns, and that's what we will work with in the rest of the lecture. Now let's look visually at the two groups. Let's see how the weight of the born baby change, the distribution of the weights of the two groups be different. Okay, how different they are from each other. So we can do that by an overlaid histogram in which we will show the distribution of the weights for group A and the distribution of the weights for group B. So we can do that by the hist function as usual with the group argument to say that I want to group by this column, which is the whether the mother is smoking or not. So when we do that, we get these two distributions. So from that, if we look at it, we can say that the yellow distribution, or brown, or gold if you wish, is a bit to the left of the other distribution, which means that on average the weight of the babies for smoking mothers is a bit less than the average for non-smoking mothers. And that's actually how the story begins. Okay, by looking at these weights, we have a question in mind. So we want to answer this question, and to answer this question, we do the hypothesis testing. So the test statistic that we chose is the average weight of non-smoking mothers minus the average weight of for smoking mothers. So to do that, let's look at the averages. We will go by the maternal smoker, and we get the average over the weights. So if we do that, we get the birth weight average for non-smoker and for smoker. You can see that there is a difference. There is a noticeable difference. This is in pounds. So for non-smoking mothers, it is for non-smoking mothers, it is 123. For smoking mothers, it is 130. So there is a noticeable difference in the weight of the babies from the sample that we got, of course. Let's see if the hypothesis testing will be supported by this data or not, or if the null hypothesis will be supported by this data or not. So let's compute. So this is computing the statistic or the observed difference. So the observed difference is 9 point something. Now let's define a function that will compute for us the difference of the means. We'll do that in a general way because as you will see inshallah in the next lecture, we will need the same function in another example. So we'll do it in a general way. The function difference of means will take three arguments here. It will take the table of the data. We'll take the label of the column for which we want to compute the averaging, which is the weights here. in this example, and we'll take also as a third argument or a third parameter, it will take the label of the column by which we want to group, which should be in our example the column of smoking versus non-smoking. What the function will do is to select these two columns. It does next the grouping to compute the averages, getting the specific array of the averages from the table, and compute the difference between the two values. Notice that item 0 here will be the non-smoking, as you see here. The item number 0 is for non-smoking, and item number 1 is for smoking mothers. Okay, and this is exactly like what we defined in the slides. So large values here means that average weights for non-smoking is higher than average weight for smoking. Okay, which will favor the alternative hypothesis. Let's test the implementation of this function. We call it with the births table, the original table, and the averaging label will be the weight label, and the group label will be the smoking label. So if we call that, we'll get 9.26, which is the same number we got here. Now let's start thinking about the simulation. Just to recall, these are the two columns that we want to play with, and the simulation now needs to do the sampling. Okay, we said that we can do the sampling by either shuffling the weights or shuffling the smoking label. Okay, in this specific example or this specific code, we will just shuffle the smoking labels. To do that, we will use the sample function without replacement. Okay, remember the sample function works on a table, and usually we give the sample size. Here we didn't give the sample size, which means by default that we want to sample the same number of rows in the table, which means it's just a permutation. Okay, that's actually why this test or this method is called permutation test. So sample without any sample size will do a permutation over the entire table, and of course we don't want to do that with replacement, so we indicated false for with replacement. So this is sampling without replacement, which means that just shuffling the existing rows in the table. So let's try to do that once. You will see that the shuffling happened. Now the rows of the table, okay, the rows of the table now are different from those. Okay, so it's just like shuffling the entire table. Now we'll take, because we said that we are just concerned with shuffling the smoking column, so we'll take that column, okay, call it shuffled labels, and we'll just stick it to the original table, okay, under a new label called shuffled label. So now the original table, in addition to that label, we'll call it original and shuffled, will have 3 columns. So these are the two original columns, and this is the one that we just generated now by shuffling all the labels in the table. Okay, now let's call the function using the new shuffled label column and see what we will get from one sample. So we got minus 1.54 from that one sample. Remember that the observed statistic value was 9.26. Okay, so that was just one sample, and this is the observed statistic. Of course, we cannot make any decision from these two values. We have to repeat the sampling multiple times as we did before. Now let's do the actual test and the actual simulation. So we have to repeat that multiple times. So we'll define a function that will do that will compute the test statistic for one sample, and that function, as you will see, will combine the code that we just went through, the code for shuffling and the code for computing the test statistic. So it starts again, it takes the same three parameters that we saw before. It will first do the shuffling, okay, and will add that shuffling column to the original table, and then compute the difference of means for that sample. Okay, so this is the function combining the two things that we just covered: sampling without replacement, adding that as a column, and calling the function difference of means to compute the test statistic. Okay, now let's try this function once with the original, of course, two columns. Remember that within the function we will do the shuffling. So if we do that once, we get 0.3. Remember the previous sample, we got minus 1 point something. Now we got 0.3. If we call it again, we get minus 1.8. Again, minus 0.34. Okay, and so on. So we need to repeat that multiple times as usual. I think this code now is very, very familiar to you. We'll do that 2,500 times, and we will plot the distribution. Of course, it will take some time because we are doing shuffling every time and computing the differences. So what we will do next is, okay, so we're done. What we will do next is to show the histogram. Okay, so let's see the histogram and do the comparison that we need to do. Here is now the histogram of the differences, the empirical histogram of the test statistic, which is the difference between the two, between the averages of the two groups. Now first notice that the distribution is centered around 0. Does that make sense? Or is that expected? Of course it is expected, because remember, the test statistic is the difference between the two averages of the two groups. And we are doing that simulation under the null hypothesis, which assumes that both groups or both samples came from the same distribution, which means that roughly the averages of them is very similar. And that's why the distribution here is 0, because the averages should not be very different. They should be similar, because they are coming from the same distribution. And remember, to do the test, we need to compare this histogram with the observed statistic. What is the observed statistic? The value of the observed difference was 9.26. So where is 9.26 here? This is from minus 4 to 4, so 9.26, maybe it will be here. It is completely outside the range of the distribution, the empirical distribution that we got. What does that mean? It means that it is very unlikely to get this observed value from the population, right? Because we repeated that 2,500 times. We never got a value like 9.26 or even closer. So it is very clear that the data and the model are inconsistent. So that's visually. So this means that, of course, we will accept or reject the null hypothesis. Of course, in this case, we should reject the null hypothesis, right? Because the data doesn't support the model, doesn't support the assumption of the null hypothesis, doesn't support the null hypothesis. So we should reject the null hypothesis, and that's of course evidence that favors the alternative, which is that the averages, there is something other than chance that affected the noticed difference in the baby weights in the two groups. Okay. Of course, sometimes visualization is not sufficient. So let's compute the p-value. How can we compute the p-value? So p-value. Call this p-value. How can we compute the p-value? As we did before, we compute the probability, the tail probability, right? The probability that the predicted test statistic is at, or in this case, higher than the test statistic. Remember, the direction of the alternative here is to the right. Okay, so it should be higher than, if that's the observed test statistics, then the tail is on that direction. Okay, so we want to get the percentage of the predicted values of the test statistic that is at or higher than the observed statistic. So to do that, we will just compare the differences values. Remember, here the array that we have the predicted values in is called differences. So differences, when it is greater than or equal to the observed difference, okay, and we want to get the number of these cases divided by the number of repetitions. Okay, what do you expect from the table? Actually, it doesn't seem that we have any case that is higher than the observed difference. Where is the observed difference? Remember, it is in that approximately in that position. So it doesn't seem that we have any case. So the value is, as you will see, the value is 0. Okay, so that means that p-value is 0. P-value is 0. 0 means it is less than any significance level that you can work with, whether it's 5% or 1%. So we can say that the result is statistically significant. Okay, so we can reject the null hypothesis and the p-value is statistically significant. Actually, it is also, we can say that it is highly statistically significant because it's less than 0.01. It's less than 1%. Let's try another p-value. Let's assume that the observed difference was here, was 1. Okay, so let's copy this and change the observed difference to be 1. Okay, and let's see what will be the p-value in this case. So the p-value, okay, same mistake again. I have to show this. So the p-value is 0.1788 in this case. So that means that at that point, the area of the tail at that point is 0.17. Okay, if that's the case, what should we do? Should we accept the null hypothesis or reject? Again, it depends on our significance level. If we are using 5% significance level, then 5% means 0.05. So that means that this value is not less than 0.05. So it is not statistically significant. So we will not reject the null hypothesis. We will actually accept the null hypothesis in this case. 0.17 is not less than, actually it is bigger than 0.05, bigger than the 5%, so we will not reject the null hypothesis. Let's try another value. Let's say that it is 2. With 2 we got 0.0356. Okay, so this p-value if the observed statistic is 2, the p-value is 0.03. Now we can, if we use the 5% cutoff, then the result is statistically significant. So we can say that the p-value is statistically significant. We will reject the null hypothesis if we use 5% cutoff, if we use 5% significance level. If we used 1% significance level, we cannot reject the null hypothesis because 0.035 is greater than 0.01. So it depends on the significance level that we are using. We compare the p-value with, and we'll see if it's less than the significance level, if it's less than the p-value cutoff, then we declare significance. If it's 5%, we say it is statistically significant. If it's 1%, we say it is highly statistically significant. Okay? In this case, it is just statistically significant because it's less than 0.05. In this case, of course, it is both. It is highly statistically significant because it's less than 0.01. Okay? With the case of 1, we didn't actually, the value was not less than 0.05, and this is not statistically significant. Then in this case, we cannot reject the null hypothesis. We will accept it. So the conclusion is, conclusion from the original experiment or original data, for which the observed difference was 9.2. The conclusion is that we will not reject the null. We will reject the null hypothesis, and of course, that's evidence that favors the alternative, which means that there is something other than chance that is behind the difference that we saw. Now, can we use the same method, the permutation test, to test causality, to say that this is causing this effect? This is, inshallah, what we will cover in the next lecture. See you in the next lecture. I'll talk to you at least in the next lecture, inshallah. Assalamu alaikum wa rahmatullahi wa barakatuh.